Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. This is the very first video of this series and on this channel, so double welcome to anyone who happens to find this. Today, we're going to get an introduction into what set theory is all about. First, we'll talk about some common applications of set theory, then we'll cover some basic definitions, and finally, we'll look at a more conceptual way to construct sets. But before I get ahead of myself, you may be wondering, what even is set theory and why do people study it? Set theory is, in essence, the study of groups of things. You already know about a bunch of sets from math class. Take the integers, for example. The integers are a set containing all the whole numbers across a number line, and the even numbers are an example of a set within the set of integers. Set theory takes this a step further and says, what if these things didn't have to be numbers? Can we make rules that apply to sets of literally anything we want? Turns out, with a few limitations, we can. So you can start to see how incredibly powerful set theory is. Because it can define rules for groups of pretty much anything, it influences a lot of other topics in math and science, such as statistics, computer science, and even mechanical engineering. The logical operators in computer science, for example, are the same as the operators used in set theory in similar branches of math. And, or, for all, and even the definition of two things being equal are all principles that come from set theory. Hopefully now you have a better sense of what set theory is and why it's worth studying. Now let's get started with some basic definitions. Feel free to skip ahead if you already know these, or if you just want to challenge yourself by not knowing what's going on. A set is loosely defined as a group of members or elements denoted with curly braces. If something is in a set, we say A is in S, using this symbol. And if something is not in a set, we just draw a slash to the symbol. A is not in S. Two sets are equal if they contain exactly the same elements. This is a very intuitive definition and doesn't really need anything extra, but a more formal definition you might use for proofs is A equals B if and only if, for all x in A, x is in B, and for all y in B, y is in A. That is, if you were to randomly pick any element of A, that element would also have to be an element of B, and vice versa, in order for the two sets to be equal. A reference guide to this notation is in the document linked in the description, which also has some example problems and other fun extra stuff. Moving on. The empty set is simply the set with nothing inside it. It's represented by this symbol. Two important operations are union, which is just fancy or, and intersection, which is fancy and. The reason they're called that is related to Venn diagrams. Each circle in the Venn diagram is a set. The union of these two sets is what you get when you unite the two circles into one big blob, whereas the intersection is only the part where the sets intersect. But you can also express union and intersection in set notation, which is what we're going to be doing most of the time. Consider some element x. X is in A union B, if and only if x is in A, or x is in B. It could be in one, the other, or in both. But x is in A intersect B if and only if x is in both A and B. And that's where these associations come from. One set is a subset of another set if it's fully contained within the other one. The even numbers and the integers are a good example of this, where the even numbers is a subset of the integers. A more formal definition would be A is a subset of B if and only if, for all x in A, x is in B. Or, any random element of A must also be in B. This looks really similar to the definition of equals, right? Well, actually, another way to say A equals B is A is a subset of B, and B is a subset of A. If A and B are both contained inside each other, they must be the same set. It's important to note that every set is a subset of itself, and that the empty set is a subset of everything. One last term to define is the power set, denoted by this fancy P. The power set of A is defined as the set of all subsets of A. For example, let A be the set of cat and 5. Then the power set of A is the empty set, the set of cat, the set of 5, and the set of cat 5. Note that the set of cat is different than cat. Cat is just a cat, but the set of cat is a set with a cat inside of it. And thus concludes the very fast-paced definitions part of this video. You can look at the example problems linked in the description for some practice, or you can soldier bravely on to the high concept part of this video. Everything I just talked about, except maybe the power set, is stuff that lower level math classes may use, because like I said, set theory is a fundamental part of so many different things. But starting now, we'll be diving into new and exciting waters, and the first water to explore is the hierarchical construction of sets. Let's start with a collection of atoms, and yes, that's actually what they're called. These are the things that make up everything else we're going to build in this universe that we live in. They could be numbers, letters, actual atoms, but for our purposes, it doesn't matter what they are. In fact, as we'll see later, they could actually be the empty set. Let's call this initial set of atoms V0. It's the very first tier in our hierarchy of sets that we're going to build. Now, let V1 be all the atoms in V0, union with the power set of V0. Let's call the elements of V1 molecules, even though that isn't an actual name for what they are. Molecules include all our atoms and all possible combinations or subsets of our atoms. Then we can combine all these molecules to make V2, which is the set of maybe all materials or something. V2 equals V1 union power set of V1. And we do this again and again to make the set of all objects and so on. Each Vn plus 1 is made by taking Vn, the previous level in the hierarchy, and unioning it with its power set. It turns out that this is equivalent to saying Vn plus 1 is equal to V0 union power set of Vn. So each level of the hierarchy is just the original set of atoms plus all the combinations of all the members of all the levels of the hierarchy below it. I'm not going to prove that right now, but a proof of that is in the example problems linked in the description. We can continue this process for as long as we want to get planets, solar systems, galaxies, and so on. Again, not real set theory terms. But even V a billion is still a finite set, because it's another finite set, V0, plus a bunch of combinations of a finite number of things. No matter how far up the hierarchy we go, we can never get an infinite set. That's really annoying, so let's fix that. Let VOmega be the union of all the sets, V0, V1, V2, etc., forever and ever. Note that we can't actually construct this set, but for theoretical purposes it's very useful. VOmega is basically the equivalent of V infinity. The reason we use omega is so that now we can say VOmega plus 1 equals VOmega plus the power set of VOmega. And we keep going the same way to get VOmega plus 2, VOmega plus 3, and so on. These omegas are called ordinals, and once I make a video about that, I will link to it here. But for now, the basic idea is that each of these ordinals, omega plus 1, omega plus 2, etc., is a different size of infinity. For the VNs, every level in the hierarchy is made of combinations of finite sets, so all of them are the same order of size, which is finite. But VOmega plus 1 has inside of it already VOmega, which is an infinite set, and all the combinations of all infinity sets in VOmega. It turns out that that means VOmega plus 1 is actually a bigger size of infinity than VOmega. I'm not going to prove that right now because I don't really know how, but I will put a link to a proof by somebody else in the description if you want to look at that. The very last thing I want to say is that a lot of the time in set theory, we're only going to talk about the hierarchy where V0 is equal to the empty set. Because it shouldn't matter what's inside the sets, cats or numbers or whatever. So by using the empty set and sets made of the empty set, we can focus on the theory of the sets themselves rather than the stuff inside them. And that concludes the first video of this video series about set theory. I hope you enjoyed it. Let me know what you think and if there's anything that would make it better. Also, make sure to check out the example problems that are in the description. Thanks for watching. See you next week.